All right, so if you can kind of take yourself back 2 days, we were looking at primarily the different protein structures at the end of Tuesday's class. And we're looking at the differences between the primary structure, that long chain of amino acids, all held together by those peptide bonds, versus the secondary structures, where we saw hydrogen bonding kind of introducing itself into the chain and causing the chain to either twist or fold into different kinds of shapes, either the alpha helix or the beta pleated sheet. And then in tertiary structures, where we saw the different parts of the protein starting to interact with themselves and going beyond just hydrogen bonding, going into creating a more compact three-dimensional shape using combination of polarity, things like hydrogen bonding, things like hydrophilic areas, hydrophobic areas, as well as some more complex interactions like the disulfide bridges that exist in cysteine molecules when they can link up together, but through those sulfurs, or salt bridges, where the ionic components of the amino acids create an ionic bond, where that NH3 plus and the COO minus create that ionic interaction between them. And then finally, we looked at just briefly quaternary structures, where we had multiple tertiary structures brought in together to make a complete protein that had some kind of biological function. So just to kind of rehash some of that, let's just go through and do some study questions here and identify, based upon the description, whether these are primary, secondary, tertiary, or quaternary structures. So a beta pleated sheet, what kind of a structure is that? That's secondary. So primary, secondary, tertiary, quaternary. So a beta pleated sheet would just be a secondary structure. What about the order of amino acids? Yep, this is primary. So yes, a primary structure just tells us what order the amino acids are in. It doesn't give us anything else about how they might interact with each other. That's what makes it primary. All right, if I have a protein with 2 or more peptide chains, keywords there, 2 or more peptide chains, that is quaternary. Because remember, each peptide chain is an individual protein. I bring in multiple proteins together to make some sort of biologically active protein. That's a quaternary structure. So this is a quaternary description. The shape of a globular protein, well, on its own would be tertiary. If we had multiples brought in, that could make a case for quaternary as well. Disulfide bonds between R groups, definitely tertiary. Remember, hydrogen bonding is the only kind of interaction that exists in a secondary structure. Hydrogen bonding is the only interaction that exists in a secondary structure. If it is an interaction other than hydrogen bonding, it has to be tertiary. So that's protein formation. What about protein destruction? Well, proteins are very biologically sensitive. They are designed to run at a very particular set of conditions. And if we go outside of that set of conditions, they tend to break down. And that breaking down process is called denaturation. And what happens in denaturation is we get disruption of the bonds and attractions that exist in the secondary, tertiary, or quaternary structures. And they can happen in a number of different ways. Similar, not quite the same. It's gone through a treatment process. But alcohols, by their very nature, should not have any kind of protein matter in it. Right, and so denatured alcohols differ from like your normal alcohols because they've been treated in some kind of way, and that usually results in a purer product. This is generally different in terms of process compared to what we would describe with proteins. When we denature a protein pretty much falls apart, becomes useless in terms of what its primary function was. When we denature alcohol, that's not usually the case. So when we heat proteins, what happens is that the hydrogen bonds that hold together those those hydrogen bonds that exist in the secondary and tertiary structures, they get busted. And any hydrophobic interactions break down as well. And we can see this in heat. We can see this through the use of some other kinds of organic compounds, where the heat rips apart those hydrogen bonds. The organic compounds can disrupt those hydrophobic interactions because organic compounds are generally hydrophobic as well. Acids and bases, because they are polar themselves usually, they usually rip apart the hydrogen bonds that exist in polar side groups. So any kind of hydrophilic interactions that might come across as a result of these polar side groups interacting with each other, acids and bases break those up. Heavy metal ions can react with the sulfide linkages. Heavy metals, we're talking about your leads, your silvers, your mercuries, your bismuths. All of those are very reactive with sulfur. And so what they will do is they will attack those disulfide bridges and basically crash out these black, nasty solids in the process. And in the process, that disulfide bridge, which was holding together the protein, disintegrates, and the protein kind of collapses on itself. Agitation can also do some similar kinds of things. So one of the places where we see this kind of thing is a really good example of this would be eggs. egg whites in particular contain a whole lot of albumin. Albumin is a natural protein. Well, we already know what happens when you heat the egg white of an egg. It changes. It goes from kind of a translucent kind of color to opaque white. Flavor, texture, they all change as well. Well, if you whip egg whites, like when you're making a meringue, that changes them considerably as well. Because you're pushing in a whole bunch of air in the process, you're also beating those proteins practically to death. And I say that not ironically, because what's happening? When you whip them, you're stretching those peptide chains, and eventually you stretch them enough, they break. And if you break the peptide chain, you break the protein, it's gone. And so when you're doing that kind of whipping, it is possible to actually go too far with it as well, where you just lose all structure whatsoever. The whole thing collapses on itself. And so we know this result. Anyone who's eaten eggs of any kind, it doesn't have to be a fried egg. Anyone who's eaten eggs of any kind knows the difference between a raw chicken egg and a cooked chicken egg. Here, chemically, is the difference. The active protein, which is all clumped up and drawn into this three-dimensional shape, when we introduce that heat, that's going to cause those tertiary interactions to start to break apart. That protein is going to unravel. This has a certain structure and a certain function. This has neither. Physical properties obviously change. Chemical properties certainly change as well. So this table here is kind of an example, just kind of summarizing all of this. At temperatures above 50 Celsius, we run into severe denaturation kinds of issues. And again, what primarily is affected is the hydrogen bonding and the hydrophobic interactions. And we see this in cooking, obviously. Now in cooking, in addition to that, denaturation also is what produces a lot of the flavor that we associate with things as well. The idea of searing meat. Well, when you sear a steak, you're basically denaturing the proteins right on the surface of that steak. You're aiding the process usually by adding salt to help draw water out of the meat in the first place. But putting it out on that high heat, on that big surface area, you're denaturing all those proteins. The result is you get that crust on the meat, which most people would say is what makes it taste really good. Without that, it doesn't quite work as well. Acids and bases, again, this is primarily a polar interaction. Organic compounds, again, hydrophobic interactions. Heavy metals disrupt the disulfide bonds. Agitation stretches the chain until it breaks. All right, we move now into the last two sections of this chapter, and they both concern the idea of enzymes. Enzymes are a specific class of proteins. So there are proteins that exist that are not enzymatic. We've talked about a number of them already. Muscle fibers, different kind, wool, fat strands. Enzymes in particular are proteins that have biological function as what are called catalysts. Now, if you've heard the term catalyst before, catalyst is something that we introduce into a chemical reaction of some kind that speeds up the reaction overall. Enzymes are basically proteins that do that kind of work on the biological level instead of the chemical level. So unlike the catalytic converter in your car, which turns the exhaust fumes into carbon dioxide, and water vapor, enzymes usually are doing some kind of biological function, something in your digestive system or in your cellular metabolism system or somewhere that's helping your body functions run at peak efficiency. Enzymes exist in pretty much all of the major functions in your body. And they work by doing something called lowering activation energy. Now, activation energy is basically the amount of energy that it takes to get a reaction to start. And then usually once we introduce that activation energy, the reaction can kind of go on its own. So an easy example to kind of think of here is, let's say that you wanted to start a fire. You get your kindling, you get your logs, you get your charcoal, you get whatever it is that you're going to start the fire with. Now, according to the chemical reaction, all that you need to start a fire is carbon and oxygen. If you got some hydrogens in there as well, God bless it. That's all you need. But anyone knows that right now I've got something here that will burn. I also am surrounded by oxygen in this room. Why hasn't a fire started yet? Because having the starting materials is not enough to actually get the reaction to go. I usually need some sort of energy kickstart to get the reaction moving in the right direction. And then once the reaction starts, the energy that it produces provides enough energy to keep the reaction going and give us a whole bunch of excess. What am I missing? I'm missing the starter. I'm missing a match, a lighter, something. Without that, this paper will never catch on fire. That's activation energy. Activation energy is the amount of energy that it takes to kickstart a reaction. And for some processes, that amount of activation energy can be really high. You require a lot of energy to get the thing going. Well, what a catalyst does is it introduces a different way of doing the reaction. It gives you the exact same results, but with a lower activation energy. So as a result, you don't need to have as high of a temperature or an increased pressure or some other kind of environmental condition to amplify the situation. And so that's what this diagram is showing. The blue reaction here shows us the activation energy without the enzyme. The purple here shows the activation energy with the enzyme. And we can see our reactants are the same, our products are the same. The only difference is how much energy it took to get there. But again, once that reaction starts, there's enough of an energy difference here that eventually the reaction would become self-sustaining, where the energy output of the products feeds back in to fit the activation energy, and reaction goes on its own. Catalysts are usually named, or excuse me, enzymes are usually named based upon the function that they perform. And so for a lot of them, basically they take whatever it is that they react with and they change the ending of that thing to ASE. So if an enzyme is meant for a very specific molecule, we would name it after the molecule. So the example here, there is a catalyst that exists. There's an enzyme that exists that is responsible for taking sucrose and breaking it down for us. Since it only works with sucrose, the name of that enzyme is sucrase. Again, we took the name of the thing that it reacts with and we changed it to ASE. Sometimes we name an enzyme off of the process that it does. So there are a class of enzymes that deal in different kinds of oxidation reactions. We refer to them kind of as a blanket term as oxidases. Oxidases do oxidation reactions. There are also some common names out there. These are the ones that do not have ASE name endings to them. They're usually where we see these are digestive system enzymes. So pepsin is a digestive enzyme. Its primary purpose is to break down peptide bonds. Trypsin is also a similar in that it is a digestion enzyme. It's geared at a very specific product. Inside of an enzyme, what we will find is that there is an area known as the active site. The active site of the enzyme is where the actual reaction takes place. And we'll get into kind of the logistics of how that works a little bit later here. But what we understand is that the enzyme itself is a protein. And inside of the structure of the protein, there is some place where the thing that we are looking to react fits. And so that thing that we're looking to react is called a substrate. And so the substrate goes into the active site. The enzyme does its work on the substrate, and the products end up popping out of the enzyme by the end of the process. So a little bit of enzymatic terminology here. Again, the active site is the region within that enzyme that is going to fit the thing that reacts. The thing that reacts is the substrate. The active site is very particular to whatever the substrate is supposed to be. So inside of it, you're going to have a combination of those tertiary protein kinds of interactions, hydrophobic interactions, hydrophilic interactions, salt bridges, hydrogen bonds, whatever the case may be. But you're going to have those present in the active site, and that's going to allow the substrate to come into the active site, be attracted to the active site, stay in the active site for the duration of the reaction. So those amino acid R groups, whether they be hydrophobic, hydrophilic, or whatever combination we know, they're going to hold that substrate in place while the reaction takes place. Once the reaction proceeds and finishes, then the substrate will be released and the products will end up coming out as a result. Now, the cool thing with catalysts, and this goes for all catalysts, is that in the process of the reaction, the catalyst does get inserted into the reaction. It does become part of the reaction. The catalyst will react with the reactants. But what happens in every single case is that after the reaction has completed, the catalyst gets spit back out as one of the products. And so what happens is that basically we have no net loss of catalyst. Every bit of catalyst that was there at the beginning is there at the end. Well, the same is true for enzymes. The enzyme is going to bind to the substrate. In the process of binding, we end up forming what is called the enzyme substrate complex. Now, that enzyme substrate complex doesn't exist for very, very long. Basically, long enough to kind of just act as an intermediary between the reactants, the substrate, and the products. So, what we will see is that there is a reversibility in this step where the substrate could come in and out of the active site. This part right here, the first part of the reaction. Okay. Tell me to slow down when you need to. So this first part of the reaction is reversible, meaning that substrate, when it gets locked into the active site, it could get out again. It's not being held super tightly. These are interactions, not really bonds. So the active site can open and close and let the substrate in and out. But once the reaction starts, and this enzyme substrate complex actually turns the substrate into products, there's no going back from that. The products don't turn back into the substrate. So the substrate can leave the enzyme. But once it starts turning into products, the products don't turn back into the substrate. Now, when it comes to what happens in terms of kind of how does that substrate fit into the enzyme, there are two kinds of ideas that are floating around, two different models. Neither one is fully accepted over the other. In fact, most people believe that both versions kind of exist. And which version that we see is very dependent on the reaction that is proceeding. So the first idea is something called the lock and key model. In the lock and key model, you have an active site that is very rigid, kind of like a lock. And like a lock and key, if you go over to a lock and you try to put in a key, only certain keys are going to fit into that lock. And presumably, only one key is actually going to fit into the lock and turn it and make it operational. And so that's the idea behind this model, is you've got your lock, you've got your key, the lock doesn't change, the key doesn't change, you put them together, and then the reaction takes place, the key, the substrate, breaks apart into the products. And so the only way that you could get into the enzyme is if you had a molecule that had the right shape. Now, the downside to this particular model is that it kind of puts a little bit of rigidity to chemical compounds that usually aren't that rigid. Again, if you're thinking about what a tertiary or quaternary structure looks like, you've got a lot of moving parts there. And you know that you also have a lot of things that are held together by hydrogen bonds or just general polar or non-polar forces. None of those are actual bonds. They're all interactions between nearby molecules and each other. And so the idea that it wouldn't move at all, that there isn't any flexibility, has some flaws to it. And so with that in mind, a second model comes about that tries to take into consideration the fact that these molecules do have a little bit of freedom of movement. And here comes the induced fit model. In the induced fit model, what we see instead is that instead of a specific lock that only fits one kind of shape of molecule, one key, we have an enzyme that has an active site that is able to flex and move and bend accordingly. Now, once the substrate is introduced into the enzyme, it does lock up in some kind of ways so that the substrate can do the reaction that it needs to do to form the products. But before that, that opening, the active site itself, has some variability, has some give in its shape. And what it allows it to do is it allows it to, as that substrate comes in, the enzyme can adjust its shape accordingly to help fit that enzyme, or excuse me, help fit that substrate as tightly as is necessary. What that indicates, what that allows for, is a greater range of substrate. So it's not this molecule works with this very specific kind of molecule and nothing else, there's now a greater variety of molecules that would be able to fit into that active site. And because the shape is able to change and lock in and create a more distinctive pocket around that substrate, the catalytic activity should increase. So let's do a quick check here. Question number 1. What is the active site? Right. The active site is a section of the enzyme. It's not the whole enzyme, but it's the section of the enzyme that actually does the work, that actually has the chemical reaction taking place in it. In this second model, the induced fit model, what happens to the shape of the enzyme when the substrate comes in? It adapts. So that's enzymes kind of from a constructional standpoint. Go ahead, Chase.
Whenever you highlight and you publish the PowerPoints, when you go back and study it, it like locks it out. It's not highlighted.
Okay. Okay, I'll look into that.
It's like I was reading the last exam, go to the highlighted part, it just the yellow line.
And you're opening it in PowerPoint or slides? Okay. Yeah, I'll have to look at that. Maybe there might be something I can do to kind of force that behind instead of from front. Yeah, thanks for bringing that to my attention. I'll look into it. All right, last section here in this chapter isn't concerning what enzymes are, but rather what they do and how they do it. And so very similar to kind of the concepts we saw around denaturation, we're going to see the same kinds of things around enzymatic activity. Because denaturing a protein would also basically make an enzyme useless. So the same kinds of things that we saw for what causes a protein to denature would also cause an enzyme to become useless. So when we describe the activity of an enzyme, what we're getting after is how fast that enzyme is able to do its job. How quickly it's able to catalyze the reaction, how quickly it's able to convert that substrate into product. But because these are protein-based, they are very, very sensitive. Sensitive to a whole bunch of reaction conditions, temperature, pH, and something we have not yet discussed, which is inhibitors. So most enzymes, because they are dealing, most of our enzymes are designed with our bodies in mind. Our bodies run at an optimal temperature of roughly 37 degrees Celsius. And so our body is designed with enzymes that also are designed to run at 37 degrees Celsius. If you go too far below 37 or too far above 37, what you see is that the maximum efficiency starts to decline to the point where if we get down close to low temperatures, stuff below room temperature even, the enzymatic activity basically falls down to nothing. And if you get above 50 degrees, proteins denature and the enzymes become useless anyway. So temperature is a really important factor here. And again, since these are biological systems, they are designed for the peak biology of their organisms. And since we're talking about human systems, 98.6 degrees, which is 37 degrees Celsius. That's the optimum. pH is also super important. Our bodies are largely regulated at a pH of 7.4. If we go too much above or below that pH, then we start to see drops in the enzymatic activity again. And the primary reasoning there is those tertiary structures are going to be disrupted. They're not going to be able to sustain the same interactions that they would have otherwise at lower or higher pHs. Now, one important exception does exist for this. Pepsin and your other digestive enzymes, they don't run at pH 7.4. The reason they don't run at pH 7.4 is because your stomach isn't pH 7.4. Your stomach's pH 2. And so those digestive enzymes have an optimum pH that matches the environment inside of your stomach and your digestive system. And so you can see it's not a one-size-fits-all kind of determination. Each one of these optimum pH values really does have an impact on based on where it is. And so pepsin, which is in your stomach, the primary purpose is to break down peptide bonds, break down proteins. Optimum pH range for it is between 1.5 and 2. You know, a lot of these ones in your small intestine, you know, vary. So sucrose has an optimum pH, sucrase, which breaks down the sucrose in your body, optimum pH of 6.2. Trypsin, which is another protein breaker, has a pH optimal rating somewhere between 7.7 and 8. So most of your body's enzymes run at 7.4. But understand, not all of them do. And in particular, when we get into some of your key organs, some of the key parts of your digestive system, those pH values can fluctuate. Which really makes you think just how awesome is your body that everything that is in it has already been kind of adapted to meet the criteria for what it is that we intake and what it is that we need. It's all set, it's all done. It's really kind of cool if you kind of step back and look at it. All right, let's take a review piece here. Sucrase has an optimum temperature of 37, optimum pH of 6.2. What would happen if we run the enzymatic reaction of sucrase at these conditions? It would be decreases for both. You're right. So if we change the pH to 4, that is considerably more acidic than 6.2. We're going to see a decrease in the enzymatic activity, possibly all the way down to 0, depending upon just how dangerous that pH is for the tertiary structure of that sucrase.
Like, will it ever, like, if you would ask the question, would we ever choose the 6.2?
You are correct. There are, so the only real circumstance where we would say something increases is if we were running at optimum and there was a deficiency of substrate relative to enzyme. So if we've got a whole bunch of sucrase enzyme and not enough sucrose to have all of them reacting at the same time, if we increase the amount of sucrose, then yes, the reaction rate would increase because all of the catalyst, or all of the enzymes would now be in use as opposed to just some of them. But that has a limit as well. As soon as we engage all of those sucrase enzymes, we are now at peak maximum efficiency at the optimum temperature and pH. There's no faster that we can go. The more sucrose we add, it's now just waiting in line behind the other sucroses to get reacted. So that's really the only circumstance where increase would even come into our thought, is if somehow we knew that the enzymes that we had were not being engaged because there wasn't enough substrate. Otherwise, the best we can hope for is no change. Chances are pretty good that if we are going too far outside of the boundaries, we're going to see decreases across the board. And in the case of B, 70 degrees is well above 50. We're getting full-on denaturation of that protein here. There's no coming back from that. Whereas with a pH of 4, possibility that if we were able to raise the pH back up towards 6.2, maybe some of that would be able to revert back to how it was and not be fully denatured. But that's not necessarily a given. Alexis? It would probably still be a decrease. So if we go to this diagram here, so, and this is set for 7.4, but if we look at 6.7, which would be right out there, it would be somewhere between no real change and maybe slightly decreasing. You would have to have a diagram to interpret that more clearly. But generally speaking, you get 1 pH unit away from optimum and we see a pretty significant drop. So again, this is at 7.4. You get to 8 and you're what, 15-20% of where it was. That's with what, a 0.6 change. Your body is designed to work in a very tight window of pHs. And so chances are pretty good that if you're going too far outside of that window, it's going to very adversely affect your ability to do the functions that it's intended to do. All right, let's talk about inhibition. Now, under the models that we had, in particular the induced fit model, the idea that we could have a molecule that is similar raises some important kinds of side questions. What inhibitors are is they're molecules that are going to disrupt the action of the enzyme in some kind of way. And they're going to do so by affecting the active site. Now, there's 2 types of inhibition. There's what is called competitive inhibition, and there's what's considered non-competitive inhibition. And we'll get to both of those here in a minute. But basically how either of them work is they affect the ability of the substrate to connect to the enzyme. If the enzyme and the substrate cannot connect with each other, then the reaction does not happen. So, competition. A competitive inhibitor is one that is close enough to the actual substrate in terms of shape, size, polarity, that it can actually fit in the active site when it's not supposed to. And as a result, it competes, that's why it's called a competitive inhibitor. It competes with the substrate for the active site. And in a cruel twist of fate, usually it's better at staying in the active site than the substrate is. So a lot of times what you'll see with competitive inhibitors is they find their way into the active site, and they stay there. They don't come out. And when that happens, obviously this enzyme that reacted with the inhibitor, that enzyme can't do the reaction. It's stuck. Now, luckily, competitive inhibitors can be dealt with. And they're usually dealt with by increasing the concentration of substrate. If we introduce more substrate into the competitive environment, the extra substrate will basically push out the inhibitor and enzymatic activity will return to normal optimal levels. So when we have large concentrations of the substrate, we get exactly what we're supposed to. Substrate binds to the enzyme, enzyme turns the substrate into products. When we have low concentrations of the substrate and higher concentrations of the inhibitor, what we see more of is the inhibitor complex, and the presence of the inhibitor complex is going to lower the ability of the reaction to take place. So using some of the modeling here, again, this is an induced fit model. So we've got an active site that is trying to grab the substrate and turn it into products. An inhibitor has a similar shape. So notice that the substrate here is kind of spherical on the bottom. The inhibitor is also round on the bottom. So the competitor is able to get into the active site and gum up that enzyme, which allows the substrate to be blocked out until we introduce enough substrate that the inhibitor doesn't matter anymore. So that's competitive inhibition. Competitive inhibition, again, we're looking at similar kinds of compounds competing for the active site. And only one of them is actually supposed to be there. Non-competitive inhibition, on the other hand, has nothing to do with the active site, at least from the standpoint of the inhibitor. What happens instead is that the inhibitor binds in some kind of way to another part of the enzyme. And when it binds to this other part of the enzyme, it changes the shape of the active site. And since the active site shape has changed, so will the kinds of compounds that can fit into that active site. The downside to this, of course, is unlike what we saw with the competitive, in the non-competitive, it's hard to reverse it because the active site isn't what is being competed for. In fact, the active site has been changed by this other inhibitor. The only way to get rid of this kind of inhibition is through some kind of alternative chemical action. We introduce some other compound that reacts with the inhibitor and gets the inhibitor off of the enzyme. And once that inhibitor gets off of the enzyme and the enzyme folds back to its original shape, then the substrate can go back in. But aside from that, that's really the only thing that would allow things to change. So again, we've got our induced fit model here on the top, showing what's supposed to happen. Here we have an inhibitor. And what happens is the inhibitor is not the same shape, so it's not going after the active site. But what it does is it attaches to the enzyme somewhere else. And notice how it changes the shape of the active site. The active site used to be wide and kind of trapezoidal. Now it's very long and rectangular. That substrate, which used to fit here, doesn't fit there. And unlike with competitive, where we just add more substrate, the problem would go away, not the case here. We would need to introduce a different chemical agent that reacts with this inhibitor to get it to go away. All right, last thing to talk about out of this chapter, irreversible inhibition. So the previous two examples are examples of reversible inhibitions, where the protein itself hasn't been directly changed. It's been altered, but everything that we could do would allow whatever altering took place to be reversed. Irreversible inhibitors actually react and change the structure of the protein itself. And in the result of changing the activity, it basically makes the enzyme unusable. Most often, these irreversible inhibitors are toxic substances, substances that destroy the enzymes that are being utilized. Now, sometimes that's a bad thing. The word toxic usually brings up that kind of thought. But sometimes that toxicity is actually a good thing, because it's not necessarily because it's toxic to us. Maybe it's toxic to stuff that is inside of us that shouldn't be inside of us. Like, here are all these penicillin derivatives. All these penicillin derivatives aren't toxic to us, but they are toxic to bacteria. So what they disrupt is the bacteria enzymatic activity and basically help the bacteria to go away. Other examples of irreversible inhibitors would be things like nerve gas or insecticides, where usually there's something involved in there that's causing chemical reactions to take place in the structure of the protein itself. And if we change the chemical structure, if we change the chemical makeup of the protein's no longer going to be usable. So in summary, inhibition can go into three different categories. The competitive and the non-competitive both deal with active site changes. For the competitive, We're looking at a different molecule binding to the active site. For the non-competitive, we're looking at the inhibitor binding to the enzyme and changing the shape of the active site. Whereas in irreversible, the whole protein gets reacted and changed and altered. All right, so let's end with this final concept. Are these competitive or non-competitive inhibitors? Well, if we increase the substrate and it reverses the inhibition, that's an example of competitive. If it binds to the enzyme surface but not the active site, that's an example of non-competitive. If it has a similar structure to the substrate, competitive. If it will not be reversed by adding more substrate, non-competitive. So that, folks, is the end of our proteins chapter, chapter 16. We made it. So now the job is this. Obviously, there's no school tomorrow, no classes anywhere on campus. So your job for the next 4 days is to start that test prep stuff. So go through the study guide, go through the practice test, figure out what questions you have and what you need to ask. Come ready to study on Monday so that we can have as good of an exam review as possible. Have a great extra day. I'll see you Monday.